Hello, and thank you for joining us today as we discuss how using composite materials can help to protect coatings during harsh and aggressive trenchless pipeline installation. My name is Matt Green, and I have the honor of leading the Technical Services Department globally for CSNRI. Pipeline coatings are the first line of defense in the battle against corrosion. Horizontal directional drilling and other forms of trenchless technology are increasingly popular options to improve safety and decrease impact on the surrounding environment. However, they also encounter increased risk for coating damage in their installation process. This presentation will focus on the prudent choice of selecting and specifying composites to protect assets in high consequence areas where coating repairs cannot be made after installation is complete. We will discuss the important features of choosing and using composite materials for this purpose, the dramatic cost savings which may be found, and view some real-world examples of the systems in use. Reliable protection of pipeline coatings can truly allow critical infrastructure to be durable for decades. To begin, I would like to give just a little background on our company and what we do. CSNRI delivers the broadest portfolio of composite and repair solutions on the market today to address nearly all asset integrity challenges across a variety of industries. Our suite of offerings include a host of polymer and resin options, along with a variety of fiber types and architectures, which can all come in pre-impregnated, field-impregnated, or pre-cured systems. Our engineering teams can design the best solution for each specific technical challenge, and we provide training and quality assurance services so you can be confident that the composite system of your choice is installed correctly to operate as expected. All of our systems have been designed to be easy to install, cost-effective to deploy, and durable for decades. While our products serve across a variety of industries and markets around the world, the primary focus belongs to the oil and gas industry. Over the course of the last 4 decades, CSNRI has built a complete portfolio of solutions designed to meet the needs of the various industries we serve. Whether it's the flagship product Synthoglass, which began its life in the marine industry, or the clock spring repair system in the transmission pipeline world, these systems have been proven over time to be reliable and effective, but we haven't simply relied on early success. We've continued to innovate and find ways to solve some of our clients' most difficult problems, even in the most demanding of situations. From extreme chemical resistance to what we are here to discuss today, the composite system, which is used as a sacrificial protection to ensure pipeline coatings remain intact during trenchless installation conditions. But before we get into any type of solution, let's understand the need for HDD and other trenchless installation methods. As anyone can tell you, disruption to daily life and safety is of paramount concern. Horizontal directional drilling and other trenchless methods like it allow for a safer pipeline installation alternative with less disruption to environment and population. The technology has allowed for pipeline companies to place pipelines in areas where it would have previously been either not allowed at all or a much more expensive and disruptive endeavor. So we have this great new technology, but it doesn't come free of trouble. The critical concern for this type of installation is protection of the anti-corrosion coating system to ensure long-term performance is achieved. And this is where composite materials come in. There are many types of damage that could easily find its way into the pipeline during this installation, and we need to be able to protect against those common issues of gouging, abrasion, and impact, as well as other general operational needs out of the coating system. Our success is determined by our ability to protect the anti-corrosion coating systems in place, both in the mainline coating as well as any field joint coatings used. But while there are some issues that come with these trenchless installation technologies, overall it is a much better solution to many of the needs in the environments it is being used. So it only makes sense to take those next steps to protect against the known concerns and ensure that we are doing all we can to put our best solutions in place to ensure safe and effective long-term operation of the installed pipeline. And in doing so, reduce or eliminate the risk of coating failure, which is our first line of defense against corrosion, which, by the way, was determined to have cost the United States alone approximately $276 billion annually from 1999 to 2001 in a study from CC Technologies. And in more recent studies, claims of over $1 trillion have made their way out into the industry. In either case, we definitely want to bring those numbers down. So what? Well, coatings have been developed over the years to provide a great corrosion protection system for the pipeline, but maybe not to withstand the stress that is induced during trenchless installations. Even the best coatings, perfectly applied, have struggled to survive some of the trenchless installs we have seen over the years. So it was a natural next step to turn to something a bit more robust for use in these conditions. In order to see what the true cost really is, we cannot simply look at material and time alone. We must also examine the secondary issues if nothing is done and coating failure is found. Each of these considerations have to be taken into account when planning to use trenchless methods to install the section of pipeline. Soil studies are completed and generally the condition is known, so a sound decision can be made as to how much risk is involved in potential coating damage during the install. The real cost in this can truly be seen in repull and repair costs associating with having to do the job again and have the site open for longer than planned. And finally, we can't ignore our responsibilities to the criteria in any applicable regulations. With that in mind, there are many standards out there today to help ensure the safe installation and operation of pipelines and pipeline coatings. But what do we do with this guidance and the requirements that we find in each of these standards? In the CFR, the statement is simply precautions must be taken. But how do we take a semi-vague statement and put it into a measurable practice? Before we look at possible ways, let's review a snapshot of PHMSA's FAQs on pipeline construction. This was based on 35 inspections conducted by PHMSA. This shows coatings are the leading issue found during pipeline inspection. Some of the most common coating concerns that inspectors noted during this was heat damage to FBE, coating over mud or rust, girth weld coating not fully bonded to the pipe, applying epoxy above or below the manufacturer recommended temperatures, and of course, the age-old issue of surface preparation. All of these scenarios can and usually does result in corrosion. If these 35 inspections were done prior to the trenchless installation occurring, how much more damage might we find if post-construction were able to be inspected in the same manner? So what can be done? That's the major question, and that's what we set out to answer many years ago as we began the development on a system to protect against these concerns. The big three, abrasion, impact, and gouge, as we've labeled them, seem to be the primary focus, but we believe there's more to do and that there is more relevant to field performance. But let's discuss these three. In the top left photo, we can see abrasion damage over a girth weld down to bare steel. During pullback, coatings are subject to continual abrasion from soil, rock, and contact between the pipe surface and the borehole. At the bending point, a pipe will also be forced to conform by bearing against the side of a borehole. The elevated surface of a girth weld will certainly experience higher abrasive forces than the smooth mainline. A Tabor abrasion test, as outlined in the diagram to the right of the abrasion picture, determines the amount of abrasion a material can endure. While lab tests show that composites are comparable to many field-applied coatings, many case studies show that the composite material prevents abrasion damage by taking the forces that otherwise would have attacked the coating. Backfilling commonly puts a coating at risk on trench pipelines. However, during a directional drill, standard abrasion or gouging can easily turn into impact when that raised weld profile, or if there are larger rocks or debris remaining in the borehole. Rocks, particularly cobble, are known to break loose inside a borehole and can impact the coating. If impact resistance is a concern, using a fiber-reinforced composite will provide significantly greater impact protection. The key point to consider is that while coatings are designed to withstand some of the mechanical damage they may see, using a sacrificial mechanical protection will always improve the results and preserve the design life of the coating. Another source of damage is gouging, also referred to as shear scratching. A rock or other obstruction protruding into the drill hole can result in a sharp gouging force on the coating. Three distinct failure modes can occur: crack propagation over time through the corrosion coating, or instantaneous penetration down to steel without pipe damage, or penetration to the steel resulting in metal loss. Any shear scratching to the coating has the potential to develop a crack that may travel and over time expose the steel to corrosive environments. Abrasion, impact, and gouge are prevalent forms of coating damage that should be considered when reviewing material properties. When using a liquid epoxy or field joint coating, the standard recommendation is to increase the thickness. which can increase the brittleness, thereby increasing the probability for shear disbondment when bending load is applied. We also see hardness values, and while some see this as a higher number equals a better number, hardness is really only an indication of the cure of that specific material. The purpose of this slide is to remind us that while properties are listed on technical data sheets, there's no real clear best choice if we base solely on these parameters. And what's worse, we cannot equate these to direct field performance based on what we've experienced over the years. About 10 years ago, the energy industry began using composites to protect coatings used on aggressive HDD pipeline installations. This application was accepted relatively widely and quickly in an industry known for being slow to change and slow to adapt to anything new. So why would so many operators be willing to take time away from their projects to look at a new type of product that's unproven and unused? Well, first of all, many of them were already pulling sacrificial pipe for visual inspection, and they needed a solution which they didn't have. So it was easier for them to say, we'll look at this on our visual inspection piece. Composite material has proven to be a more reliable source than pipeline coatings alone, based on the results observed in numerous HDD thrust bore and direct pipe projects, and they were used on many of these in the field as trial samples. Lab results showed little or no difference in abrasion impact or gouge testing between these two types of materials, while the field trials showed very different results. For many years, the composite materials have been applied to the leading edge up to the 300-foot sacrificial sections for the visual inspection. And why were so many people interested in doing this? Because they didn't have a reliable solution that could be repeatably used and be confident. And they were being installed in some very high consequence areas. So they needed a solution, and they needed it now. But for years we asked, why don't the lab reports tell the same story as the field results? Finally, we looked at fracture toughness. Fracture toughness measures the ability of a material to resist fracture. In this graph, we can see the red circle represents the estimated strength and toughness of common rocks, and the blue circle represents the epoxies used to protect our critical infrastructure. I would consider this overlap as our no-go zone, as we can see that epoxies have comparatively less strength and toughness than the rocks. In the green circle in the top right corner, we can see that FRPs are generally stronger and have a far superior fracture toughness. And right in the center of that circle is the GFRP, or glass fiber reinforced polymer. While Lehigh University publishes this graph online, we wanted to see if this property could explain why we've seen over a decade of superior results using composite materials as compared to standalone liquid epoxies. To perform the test, specimens were pre-cracked, then a tensile machine takes the sample to failure. The ability to resist fracture is calculated based on the results. We selected 2 commercially available liquid epoxy fill joint coatings and several iterations of composites to perform these comparative tests. The test program showed that composites are 10 to 30 times stronger, 10 to 20 times stiffer, and overall composites possess 10 to 15 times greater fracture toughness than standalone epoxies. This was finally a lab report that validated what we have been witnessing in the field for so many years. So the solution, which we have been discussing, was developed based on years of experience using composite materials for repairing damaged pipe. It was such a simple idea, but has had an immediate and lasting impact on the successful implementation of trenchless installation methods and maintaining coating integrity during the process and for the lifetime thereafter. The beauty of a composite material solution is the flexibility and versatility it provides, not only in how it can successfully function, but in how it can be custom fit to the specific needs of a project. Faster or slower curing resins may be chosen based on the needs of the environment, or a completely different resin may be used depending on how aggressive the borehole may be. Whatever the combination, using composite materials to protect the coating, both mainline and field joint, has proven to be extremely effective both in implementation and in economics. And speaking of economics, this graph represents a 20-inch OD pipeline that was pulled in an HDD project for 3,800 linear feet. In the first column, titled Traditional, you can see the cost of the project in total, which did not pass post-construction coating inspection the first time. So it was decided to use the ScarGuard system, then repulled. The second column, titled ScarGuard, shows the overall project cost using ScarGuard from the start. And finally, the third column is the total savings, and this shows the money that could have been saved if the composite material was simply specified and used upfront, rather than having to repull and do all the work. Too many times, only the material cost alone is compared, and residual costs are not considered. Estimates show that anti-corrosion, abrasion-resistant, and field joint coatings represent only 3 to 5% of the overall project cost. This is a small price to pay to basically ensure success of your pipeline coating, which ultimately ensures the integrity of your pipeline. And as mentioned, we've had many field successes using this type of material to protect pipeline coatings. This specific project, I was lucky enough to be able to visit on the job site. This occurred just as the world was shutting down due to COVID in early 2020. The project called for a full encapsulation of the 20-inch OD pipeline for a total length of 11,000 feet or 3.35 kilometers, and they were in a time crunch. They needed this to happen very quickly. We arrived on site. We were able to train a crew of about 8 installation technicians with the contractor, and within only 3 days, including a rain delay, the entire project was complete and they were pulling the pipeline through the borehole. So this goes to show that you can get the material. It's very quick, it's very versatile, and it's very easy to implement on site, even when you need things to happen fast. There are many more case studies like this that we can show, and we would certainly be happy to do that if you're interested in furthering the conversation. But for now, we're going to wrap up. The trenchless technologies available allow for a much less invasive and disruptive installation of pipelines, but they do come with their own set of risks, and this manifests heavily in potential damage to the pipeline coatings. Composite materials have proven to be a highly effective and economically viable method of protecting those coatings in many aggressive conditions that may not have been possible before. Using these, we're able to help the industry continue to push the boundaries of what is possible, while also maintaining and even improving the safety and effectiveness of the final installed product. Based on the history of testing, validation, and successful field use, you can be confident in your decision to use composite materials to protect your coating systems. Thank you again for taking the time to listen, and should you have any additional questions that may not be covered in our Q&A session, please feel free to contact me at any time, and you can use my email address that you see on the screen there. I appreciate your time and look forward to hearing from you. Thank you.